works well. It also works well for us. Yeah.
Okay, let's get started. I feel like the number of students has decreased drastically. Right after this or before? After. So you guys are prepared, right? Oh, that's good. Then you should interact more. I know you already interact, but yeah. So which class is that? Machine learning. Yes, 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 yes. That's a tough class. This is an easy class compared to that. Yeah, you guys should try the machine learning class, which is going to be way harder than this class. That has more structured, like you really need to know the details. Here you can get away with not knowing the details, but the good thing is this is an elective course. Okay, so you explore. You don't have to be really good at all the topics that we cover in the course. You pick, let's say you want to be in vision. You kind of understand the vision topics better than some of the other topics that we're talking about, like text today. If you're never going to deal with text, if you're not interested in text, it's fine. Just know the lay of the land. It's fine, right? Same thing with the second part of the course, or I guess the last 4 lectures are going to be about sequential decision making, where you kind of mix predictions, which is what we've been seeing in ML and deep learning, with decisions. Okay, it's something that unless you are in operations or something like that, you will probably not be interested in decision making directly unless it comes in your research or something. So just pick and choose what you would like to learn, but learn that at least those well. Other ones you can just get a sense of them through the lectures. Okay, so where are we? We are on 21st. So assignment 2 was due yesterday, and I will go over assignment 2 questions very briefly right after this. So assignment 3 is the next one, and for that, today's lecture will be pretty much the only lecture that's going to be useful for that. Okay, so today we'll be spending a little bit more time on the word embedding idea, and then we'll go to the sequence models or time series type of models, and that's the content of assignment 3. And it says here you want to work with what is called a language model. This GPT-3, 3.54, they are language models, and obviously the chat versions of it. But we've already seen an example language model, a Markov language model, which was at the character level. So that's what language models are. We can revisit that today. And translation. So this is like a sequence. You get an input sequence of words in English, and you want to produce a sequence of words in Hindi or some other language, right? So that's the assignment. There are 2 questions in that assignment. So that's 2 weeks from now, but the content is just today's content. Okay. So let's actually talk about assignment 2, and then I'll talk about the lecture goals, and then we'll get into the slides. Okay. So assignment 2, question 1. I think I already gave a hint before a couple of lectures ago that you just need to kind of go through the ants versus bees example that's one source. Okay, there are many opportunities to figure out how to solve the problem, but one of the pathways to at least answer question 1 is you go through the ants versus bees notebook, because it has both the fine tuning and the fixed feature extraction parts, and basically it's about preloading a reasonable model, SNet 18, and changing the last layer, and then freezing the weights and unfreezing the weights. But the big delta, hopefully, that you learn is the pattern in which you lay out like a PyTorch-based supervised learning problem. Okay, so obviously there's images involved, so there was torch vision related objects that you also had to create, but it's very similar to, I guess it's a little bit more low level compared to scikit-learn, right? Scikit-learn, you import a model definition and you just say fit, transform, or predict, or whatever, right? But the pattern that you observe with question 1 is the same pattern that you will see if you ever had to do other models. It's, maybe instead of images, you have something else, a little bit different data pre-processing steps, but after that, everything else will be very similar. Okay? But the second big challenge with question 1 is actually tuning CIFAR 10 on, CIFAR 10 data. doesn't require, but it actually makes it very convenient if you have a GPU or some accelerator with you. That's why if you do it on Collab, at least you can get some of the free resources.
But it take a whole hour to execute only first question.
Yes, so it takes time. So how do you scale down, right? So it's very hard to scale down because ResNet 18 already kind of predetermines what is the resolution, what's the last layer. Let's say you're doing fixed feature extraction, it already predetermines what the last layer's dimensions are, right? 10 outputs, but like the inputs are going to be 1024 or something, or 512, I don't remember. But yeah, so those many numbers you need to train, which is non-trivial. So if you don't have a GPU access, but if you do have M1, M2 Max, sometimes they have some accelerators for that. Also, you can use the integrated GPU. No. Kernel died because of various reasons. One of them obviously could also be out of memory errors. But I don't know if in this case it's out of memory. Not sure. So yeah, the big challenge with question one is, in addition to learning PyTorch and the pattern, it's also like you really face the issue, especially if you've not tried out GPUs and you're only thinking of CPUs, then it's like a hard thing to do. Yeah, I don't have a quick fix for this. If you have access to a GPU, even a low powered one, like even if you have a GPU from 5 years ago, it'll work for this. Okay, yeah.
At least for M1 Max, TensorFlow is pretty optimized.
Yeah.
Torch is still pretty slow, even with like M1 graphics card.
Okay.
It's still not as fast.
Yeah.
Compared to the CPU.
Yeah. Okay.
At least that's what happened to me.
Okay.
I did try CUDA on my brother's gaming PC.
Yeah.
Like an NVIDIA graphics card, and it still was pretty slow, but his graphic card was like 3 or 4 years old. Yeah.
So yeah, I mean, older graphics cards are still going to be better than, let's say, this year's CPUs, just because the workload, the pattern of computation is mostly matrix vector multiplications or matrix multiplications, which are more efficient there in GPUs. Okay. For us, it's a black box, but if you want to, I mean, we haven't discussed GPUs in the class, but it's good to kind of know why are they better than CPUs. Okay, what do they do that CPUs don't do? It's got to do with how memory and compute is laid out next to each other in GPUs, and there are actually a lot of small computation units. It's like a grid of memory, compute, compared to like a CPU setting where there's a very, very high powered CPU, but there's some caches, but then there's a RAM, which is where you access data, push data back and forth, and there's some latencies there. Okay. Actually, some companies are actually trying to see if CPU-based trainings can actually compete with GPU-based training. Okay, obviously you need some tricks to actually achieve that, even be in the same ballpark. But some firms are trying to do that because there's a lot of CPU hardware availability. So innovate on how to fit your model training on that, and that requires some tricks like specifying the number of computations needed and so on. Okay, but companies are trying to do that. Anyway, first question is pretty standard. I don't have anything else to add, but did you guys have anything to add here? Okay, the second question,
I actually do. There was one training image of a cat, but the cat was in a toy car.
Yeah.
And they classified it as a car. The company's very funny.
The cat had a toy car, so there was a car.
A cat inside of a toy car.
Ah, okay.
They classified it as a car as opposed to a cat.
Okay. Wow, the 32x32 images are so small that it's hard to kind of identify objects in there. So there's a lot of mislabeling, by the way. So CIFAR10 and these types of data sets, MNIST and so on, they're all very, very highly, so many people have looked at it that they're very good. But a lot of data sets, even really popular ones for, let's say, object detection, which was a theme of last semester's projects. All projects were all about object detection. There's a standard data set called MS COCO, which has 80,000 classes. Sorry, 80 classes, and like different people and objects and so on. There actually can literally see in an image that either you've misclassified or missed an object that you were supposed to classify and so on. Okay? And this is like a very popular data set. Like in fact, it's like the exponential distribution where it's like the MNIST of object detection. Okay, and then you can imagine for any domain specific data set that some researchers have collected and annotated, there could be so many errors. Okay? And it makes even more sense, even more of an important thing for private companies. And so actually there are actually billion-dollar companies with just two annotation. Okay, yeah. So just people, they hire people and they'll annotate your data for you. Yeah. So let's talk about the second question, because this is where, if you have not seen a solution before, then this is where you want to think of how would I set up this problem. Okay. This is actually related to the embeddings. So I know we didn't cover the entirety of embeddings last time, but this gives you something to think about in terms of how do I lay out my, the four components of the classification problem, at least that we discussed. It doesn't exactly map it that way, but you can, right? You can think of what's the data, what's the model, what's the loss function, and what's the optimization technique. I guess optimization technique will not worry about. What's the data, right? So in this sentence here, before the 3 bullet points, there's already a description of what the objective function is. And so obviously the objective function should have data, right? So we have this objective, we want to either minimize, maximize, whatever, and there's data part of it, right? So the data is here xij, and so there has to be some pre-processing from this zip file or whatever this movie review information to get xij. Okay, there's some pre-processing needed. And how do you do that efficiently? Like, will you write multiple for loops to get this xij? What is xij? How are you going to define it? Is it precise or not? That's just creativity. Okay, there's no right answer here. So what is in the sentence it's saying xij be the number of users that like both movies I and j, right? So if you had access to who are the users who like movie I, sorry, and who are the users who liked movie j, in the sense when I say who are the users, let's say user ID. Okay, so let's say you have a list of user IDs for I and a list of user IDs for j, then you can just do some sort of make them into sets and then do a set intersection or something like that, right? At least you get the set of users, and then you can also compress it into size of the set. So that would be the number of users who did something with movie I and j. Whether they liked it or not, that's something that you need to decide. Whether what does it mean by liking. Maybe you say, okay, a user I likes a movie if sorry, a user whatever, I don't know what the user next. Let's say user U likes the movie I if the rating is greater than 2.5. Let's say you decide. And then the original list actually shrinks to, among the users who did rate something for the movie I, how many actually rated it greater than some value. I think maybe the mean of that movie ratings for that movie are 2.5, for example. So you need to decide that. Okay. I mean, there's no right answer here. You decide. And then obviously computing this depends on how many for loops you write, and it's going to be inefficient if you write it in a inefficient way. Yeah. Group by, but okay, yeah, pandas group by. I mean, I don't know. So it depends on how we implement it, and if you implement it in an inefficient way, then yeah, it will take more time. Yeah. I mean, you need to at least loop through everything twice, right?
Yeah, but it's just the number of movies that you need to look through.
Yeah, that's true. But aren't there, how many movies are there? I thought there was 1,000 movies. Is that not? Yeah. Okay, I mean, some students might face some challenges in just finding the xij matrix. And the question is, would you even represent it as a matrix, or is it a sparse matrix? Will the other entries where, let's say there's a couple of movies where no users were common, will you put a 0 there, or will you just keep it empty? Okay, so there are some questions like that. I don't know, how did you guys answer it? Did you make it a dense matrix? Because then it's a 1,000 cross 1,000 matrix, which is not big, but it's not too small. What's it?
Like a data frame, like movie 1, movie 2, the
number
of movie ID, and then the users xij.
So if there are no common users for I and j, there is no row in your data frame.
No.
Oh, there is a row, but you're saying it's a 0. So it's 1,000 plus 1,000, so a million rows in that data frame, and then you're saying for every pair there is almost a million rows basically. maybe half that, like n times n minus 1 by 2. And then for each row, you're saying how many users liked. Yeah. No, I'm not saying, by the way, so my question was more about there was no commonality. What would you put there? Right. So there's no right answer here, because if two movies are completely different genres, then and therefore maybe they they attract very different types of users and audiences, then why does it should you put a 0 there? 0 means basically that there are no common users, or maybe there is an audience which likes both, let's say genre 1 and genre 2, but it's just that they did not see this movie. So basically you're imputing value which is not there. Okay, we did not observe anything either on the positive side or the negative side for this pair of movies. You, by deciding to put a 0 there, you are actually doing some sort of imputation. Okay. So my suggestion is, if you don't want to impute, then you can also, it's not going to stop you from continuing on, so you should not impute unless you have a strong reason to do so. Okay. Because I don't think, you're just summing over everything, so you could skip, okay, there's no data for a pair of movies, then that term is not there. Okay. Okay, so let's say we created Xij, and therefore we can, for any for any collection of these vectors, there's one vector per movie, we can actually compute this number, right? That at least that should be clear. Like if somebody told you, hey, here's a vector for movie 1, here's a vector for movie 2, and here's the vector for movie 1000, and data is already there. So given those vectors, I can always compute some number which is just a function of those vectors, right? Take the pair of vectors, inner product them, and just see how different they are from the Xij value, right? So, and then the objective is actually to optimize these vectors such that this C function or whatever the objective function is minimized, right? So we are optimizing vectors. It just means that parameters of vectors are now are basically the parameters of this model, and they need to be optimized. They need to be changed so that you get to the bottom of whatever the loss function is here, the square loss function, right? So given this description, now you want to map it back to PyTorch. How are you going to, if you use PyTorch? You don't have to use PyTorch unless I said so. Yeah, how do you map it back to, let's say, PyTorch pattern, right? PyTorch has, okay, there's a model definition with a init and a forward, some functions in the model class that you derive, and then you can write your do a forward pass every time you call the model on some input, and check, and then you call the loss, and then you do a loss.step and backward and so on, right? So that's the pattern. How does it fit with that? Is you could think of I and j as inputs to the model. Given I and j, it will go back and say the model here is just the collection of these vectors, right? So the model, given two indices I and j, will say, okay, oh, this said the input was I and j. Let me go back and fetch the vi vector and the vj vector, multiply it, and produce an output. That's my prediction. Okay, that's it. The model is just taking two indices and then predicting. That's one way to think of a model. Taking two indices and producing a number, and that number you just want it to be close to Xij number. Okay, so targets are Xijs, and the model is predicting a number which hopefully is close to Xij. So, and then since Ij is a input, you can say, okay, how do I can batch it, so I can generate a batch of Ij pairs and then pass it to the model if you want, or you can produce all the Ij pairs that are that you can predict on, and then pass it to the model, right? So any questions? Have I lost everybody, or did anybody face any challenge with this question? I guess that's, let me ask that. So it's a problem where I think it's just a question of, if you are creative, you can always get to some solution. Is the question is, are you confident about what you've done? Okay, so there's so many choices, few choices, not so many, but few choices you need to make that may, make you feel like, okay, I'm not confident whether I'm doing is correct or not. But All I'm saying is, as long as you're generally clear that, okay, I just need to tune the vectors, and you know, for a collection of vectors, find a collection of vectors such that this objective metric is minimized. That's what you want to do. There's some design choice here also, which I did not point out earlier. This is the vector length. What should be the length of this vector v1? What should be the length of this vector v2? Should it be 10 dimensions or should it be 1,000 dimension vector? Okay. Why should it be 1,000 dimension vector? Why should it be a 10 dimensional vector? You should think about this. Okay. 10 is easy. If it's just 10 dimensional vectors per 1,000 movies, then it's 10,000 numbers, which is a lesser number of parameters to optimize for. But if you're doing a 1,000 dimensional vector, then 1,000 times 1,000, a million numbers to optimize for. So the problems are going to be different. But if you do a 10 dimensional vector, then maybe you're not able to predict Xij that well for the Xijs that you know for some pairs of movies. But if you use a bigger vector, then maybe you're able to fit, you can reduce the loss value. Okay, you can get to lower and lower values of C. Okay. Anyway, so these are things to think about. And finally, obviously, the last point is just some sort of nearest neighbor search. If you already have the vectors, then given a vector, you can always find other vectors. But obviously, here the problem is a little bit different. It's giving 3 vectors or 3 movies for which you probably have vectors, and asking, what could be other recommendations. So basically, you have 3 movies. You can find neighbors around them, or you can find, find like an average of those 3 vectors and find neighbors around them. In any way, this is again a creative part. You can justify any approach you want. Any questions or comments about this? Yeah.
Like here in part 3, we actually did 2 versions for the solution.
Yeah.
Like we recommended there's only 1 movie, like for Apollo 13, we
Yeah.
recommended 10.
Yeah.
And then another version where we took the 3 movies together.
Yeah.
Recommended based on the 3. So we have to take all of them or just one by one?
That's the thing, right? Given movies A, B, and C, the question is also, kind of ambiguous. Yeah, you could generate 10 recommendations given this movie, given this movie, given this movie, you would have 30. Or you could just generate 1 and say that's the way you generate. Or you could generate 3, 3, and 4, and then just concatenate if you interpret. It depends on how you interpret this question.
Actually, then both.
Yeah, so not just that, right? So there are more than the 2 options you said. There could be many ways to kind of generate these recommendations. Okay. So this question is mostly about also kind of this intentionally ambiguous, so that you can be a little bit more. This is how it's going to be in practice, when your domain specific problem will not map exactly to a well-known tool or a well-known approach. Okay, so you'll have to do some choices, and some choices will be kind of off, like the imputation that I mentioned. If you impute, then you better have a good reason for Xij to be equal to 0 when there is no users common for INJ. No users have seen both INJ. Okay, any comments before I move to the lecture goals? Okay, then let's talk about today's objective. Today's objective is so we'll kind of I know there's going to be there's some slides that I will put on the back burner, which are about generally use of embeddings and so on. But today's one of the core objectives is to kind of have one clear implementation of these vector embedding that I introduced last time. Okay, these word embeddings that I introduced last time. Last time I was just motivating it as, okay, we just want representation of words, representations as in vectors for words, which kind of capture the semantic meaning of the words, which means that words that appear in, what we want actually practically is that words that appear in similar contexts, we just want them to have similar vectors. Okay, that's what we want in practice. Obviously there's some motivation to why we want that, but that's in contrast with, let's say, one-hot encoding or other approaches where you're kind of ignoring semantic information in the words. Okay, that's what we want. We want words with appearing in similar contexts. They need to have similar vectors. Last time we saw some motivation of how to get such a thing, by just constructing some auxiliary random prediction task. And if we do well on the prediction task, then maybe because the vector embedding portion is also part of that forward flow, because you want to start with some words and then get to the prediction, and then last time the example was something to do with a valid sequence of 5 words versus an invalid sequence of 5 words, where these 5 words were fetched from Wikipedia, and it was a binary classification problem. And if you do well in binary classification, because there's the W transformation which was going from a word to a vector and was part of that forward pass, you could optimize the parameters of W as well, which would, the parameters of W would be what leads to a good embedding. Okay, that's what we saw last time. I'm gonna show the slides in a second so you can recap. I will not recap the general problem. Let's actually specialize it to word to vec, just so that everything is very concrete of exactly what the problem this Google research folks did 10 years ago, and how they got these embeddings. Okay, and then they shared those embeddings. It led to a good improvement in many applied problems. It's called word to vec. These are going to be what are called static embeddings. Okay, and so next lecture, in lecture 6. So today is actually before getting into lecture 5. These are going to be what are called static embeddings, as in you create a vector for a word, and it's the same vector irrespective of which context the word appears in. Okay, and we'll see 2 lectures from now, which is the kind of actually next lecture. It's called a different architecture, some model, again for text processing, where these you will still get embeddings for words, but they are contextual. Okay, so if the same word appears in sentence 1 and sentence 2, and both sentences have some different, mean something different, then the embeddings of the same word will be different. Okay, so those are what we'll see later. It's just a teaser. Let's not understand it right now. Sorry. Yeah. So today's objective, word to vec. Next objective is actually to kind of look at a class of problems and a canonical model, which is going to be now different from word embeddings. But word embeddings are nice. They can be used for the next collection of models. So the next collection of models we'll see are called recurrent neural networks. Will not look at transformers today, but RNNs, and they are useful for essentially time series like problems. Okay, and one I guess popular RNN architecture is called an LSTM, and so we'll know what LSTM is and how it works. Okay, so again, how it works just means what does a forward pass look like, because forward pass pretty much tells you what computations happen from the raw data from raw input to some prediction, right? So that's the goal for today, to just cover word to vec, and then just wrap up vector embeddings and word embeddings, and then talk about sequence models. Any question about this lay of the land? Okay, we'll get into the detail then. So yeah, so I'm not going to go through again from slide 32 linearly. I just wanted to flash a couple of slides that were relevant from last time. So we want to learn. Okay, let me start from this slide. We want to learn words are not numbers, right? Obviously words are composed of characters. Characters, if you actually look at their representation in the computer, is a bunch of at the end of the day, even numbers are all represented using bits and bytes. Okay, so there is going to be some representation. It's just not numeric that we think of. Okay, so sure, the letter A maps to maybe the number 26 or 27 or whatever, or number 97, doesn't matter, but that's not the way we want to transform words. Okay, so what we want is a transformation that goes from words to a vector space such that this word-word relationships are preserved. Okay, similar contexts, words that appear in similar contexts have similar vectors. Okay, that's what we want. And the question is, how do we learn that? And the answer is, we'll start with whatever be this W transformation, and in fact we'll see that the W transformation is exactly just a matrix. Okay, so it's just a linear transformation in the sense that given a word index, you spit out a vector. Okay, so the input. So if you have a bunch of words, as long as you know what is its index in the dictionary, you query that row of that matrix W, and that's your vector for that word. Okay. So it's a, so in terms of representation of this function W, just think of it as a matrix. Okay. With indices being so every row index corresponding to the whatever the index of the word was in the dictionary, okay, in alphabetical order. So we start with some arbitrary numbers in that W matrix, and then we want to learn it along with we want to learn it so that we actually get good vector representation. And for that, we want to have some auxiliary task on which we know how to train some sort of binary classification, and we do well in that task, we will also get good representations for W. Okay, and one of the ways we were doing it was some classification problem. I don't want to repeat this because we're going to look at word to vec and we'll have a specific classification problem. But basically, if you had, let's say a valid sequence of words, then since these are going through and picking up the right vectors, picking up, the vectors for those words, and then those vectors are being used to do the classification. If you do well in classification, that means that hopefully, the hope is that if you do well in the classification, you do have good vector representations. Okay. Now, it's still not clear why this would doing something like this, some random classification, some auxiliary task. Still not clear why it will maintain some semantic information. The similar context means similar vectors. It's not clear at this level, and so let's look at it with a specific implementation, which is the word-to-vec implementation. Okay. So I'll skip over a bunch of slides, which we saw last time, but some of these steps are I don't want to get into before we talk about a concrete implementation. This is just talking about some uses of embeddings and different types of embeddings. But let's actually talk about a specific embedding, okay? Because it's basically the specialization of that example that I showed earlier. So it's actually 10 years ago. It's a method for getting these vector representations for words. Okay. So we're thinking of words, by the way. So if you have categorical variables, you can also do the same. You can get a vector representation for every category value for your categorical feature. Okay, same way. So yeah, so the distinction to a count-based method, which we did not discuss at all, is that there are some other ways to also get vector representations which capture the hypothesis, the distributional hypothesis we wanted, which is similar vectors for similar context, words that appear in similar context. You can also do some other approach, which is count-based, which is exactly what the embedding problem that you solved in assignment would do. Like, it's like for every pair of words, see how many similar contexts they belong, they appear in, and once you get that X matrix, which says, okay, for a word I and J, how many similar contexts do they appear in? Then you can get the VI and VJ for those words by exactly solving your assignment 2 question. Okay. So it's actually, you can map it to your assignment 2's question 2. Okay. But we will not discuss that. What we want to do is a predictive method. So we want to have some auxiliary prediction problem and then learn good embeddings. And this time we'll actually reason why we got good embeddings, as in good in the sense of similar contexts, words in similar contexts get similar vectors. Okay. So that count-based method, or even the assignment 2 question, what you actually computed is co-occurrence statistics, right? Co-occurrence, how many common users liked both movie and engine, right? Okay, so let's actually. So word2vec has, it turns out, it has 2 ways to describe the same thing, and we'll describe it in one way, which is called the skip-gram model, or skip-gram description. There's a model, obviously, but there's also a continuous bag of words model or setup. Okay, these are what are we setting up? The auxiliary problem, the auxiliary classification problem, and both are so similar that there's no need to kind of there's no difference between them, in theory, but there's slight difference in how it's described. So we'll stick with one way to describe this word2vec training process, which is called the skip-gram model. Okay, and we'll see why it's called a skip-gram model. Okay. Let me actually make it full screen. Okay, so we have a classification problem that we want to do well on, and as a byproduct, we want to get the word vectors. Okay, so what we'll do, we'll actually train a single hidden layer neural network. So the type of neural network we saw in lecture 1 or lecture 2, right? And then we will actually, by just training some network like this, and we'll obviously I'll specify what the input is, what the output is, and so on. But just training a single hidden layer neural network, we'll be able to interpret. Remember, one hidden layer neural network will have two sets of weights. There are W1 and W2 that we use in lecture 2. So one of the weights we'll just interpret it as our embedding matrix, or the embedding W matrix. Okay. So let's actually first talk about the task. So the task is very similar to the example task that we were discussing before. So the task is you have a sentence. Now we're not talking about the sequence of 5 words in Wikipedia. Let's say you have a full sentence, maybe has 10 words. You pick a word. It doesn't have to be in the middle of the sentence, as the first point says, but you pick a word, and then you pick one of the nearby words at random. Okay, nearby to it, and then what you picked a word, and then you picked a nearby random word. Now these two form the input-output pair. Okay, so what you're trying to do is, given the chosen word that you picked, it can be in the middle of a sentence, it can be somewhere in the sentence, and then you pick the nearby word. Given this word, you're trying to predict the whatever random word you chose in the neighborhood. Okay, so you pick two words. One of the words will be input, one of the words will be output. Okay. So what does it mean for so here I'm saying input is a word pair, but it's actually just our input as in our example, sorry, is a word pair. And obviously the network produces a distribution of scores, right? So on the output, so what is the distribution? It's going to be a distribution over all the words in the vocabulary. Okay? Because remember, we want to predict a word, and there's so many words in the vocabulary. So whatever is the number of words in the vocabulary, there's going to be a distribution on it that the model predicts. So it's like same thing as CIFAR 10, or imagine a 1,000 class. Instead of 1,000 classes or 10 classes, it's 50,000 class classification. Okay, so it's a really too many classes, but nonetheless, it's a classification problem. Okay. So nearby, so the way I described it is a little bit, not very precise. Nearby, let's say we say, okay, let's, for every word, let's talk about a window. Window just means like we want to kind of say what is nearby, like some interval. So we'll say, okay, for this word, the one word preceding it, and maybe two words preceding it, maybe the two words preceding it are considered nearby, and two words succeeding it are considered nearby. Okay, so therefore there are at least 4 words from which you can pick one of them, or you can pick all of them as to create your examples. Okay, so here's the example sentence: the quick brown fox jumps over the lazy dog. So let's pick the third sentence, just so that this word, let's say our reference word is brown. Then these two are considered nearby, and these two are also considered nearby. And from that for this reference word, we'll have 4 examples. Okay, so brown, want to input brown and want to predict the word D. Input brown, we also want to predict the word quick, and input brown, we also want to predict fox, and a brown also predicts jumps. Okay? So we say, okay, for the same input feature vector, why are we predicting 4 different classes? That's maybe the first go it seems strange, but it's not, right? So a regular classification problem, you could always have examples where for the same feature vector, you could have 2 different classes in your training data. Okay. So and the previous couple of sentences have a little bit of an edge effect. So there's only one word on the left, so they only generate 3 examples, and this word doesn't even have anything on the left side, so that's why I'm only generating 2 examples. Okay, so the rightmost side is what's showing the input-output pairs. Okay, so if I give this as an input, I want to predict brown as an output. How do I predict brown as an output? When I produce the distribution over these 50,000 classes, let's say my vocabulary size is 50, then the index of the brown word should have the highest probability. Hopefully, that's it's just a 50,000 class classification. Okay. So let's focus back on the network. As I said, the network is yeah.
I think the word also have change the value for the
No, it doesn't have to be, right? So we just want, so these are a little bit contradictory examples, right? So if I want to have highest probability on D, then why wouldn't I have high probability on quick? That's true, but when I'm, so think of like when, loss, in classification loss, the loss is per example. So for this example, for this word, I want high probability on this one. If I have low probability on this one, the loss on this example will be high, right? But I don't need to have equal probabilities on all of them. Okay, I mean, equal probabilities can happen, sure, but that's just the nature of how you set the. I mean, that's just a consequence of your optimization that it may lead to equal probabilities on those 4 words. Okay, and also Brown doesn't only appear in this sentence, right? Brown can appear in many sentences, and they all may have different neighborhood words, right? So, in effect, although the examples are a little bit contradictory, as in like we want different words to have high probabilities, basically think of it as given the word Brown, you're basically trying to surface those words that appear in its neighborhood to have high probabilities and everything else to be low probabilities, right? And similarly, let's say there's a word red. We want all the neighborhood words of red to have high probabilities and essentially roughly have high enough probabilities compared to everything else. Now the only question is the context which red appears in and the context which brown appears in. If they're common, then these 2 clusters of words where there has to be high probability should be kind of common, right? So that's where we're going in a few more steps. Okay.
So here the window size will affect like for the prediction.
Yeah, window size is yeah. I mean, so what's the definition of context, right? So nearby, yeah. If your nearby is instead of 2 words left and 2 words right, instead of it is 8 words left and right, then it's a longer context and maybe maybe it's a looser context, but that's a choice that these guys made when they developed this. Yeah, so there are a lot of design decisions going on every step. I mean, so don't get stuck on like, okay, why did they make this decision? Some of the decisions are actually, they had to make some decision. They just chose the neighborhood size to be 2, and there are some good reasons for that. But all I'm saying is there are decisions that are being made. Some decisions are intuition. There's an obvious intuition. Some decisions, if there's no obvious intuition, sometimes it's probably just driven by some empirical observations. Okay, where intuition may be a little bit, post hoc in the sense that, in hindsight, you can reason about anything, right? Okay, yeah.
Just to clarify on understanding, so in this case, the input would be like Brown, and then there's the probability of quick front box or John.
Yeah, so given the input Brown, we'll see the network. It's just a one hidden layer network. Given the input Brown, we want to get a distribution over all words in the dictionary, where the index for the word D, whatever probability it is, it's high. For this example, obviously, if I make that's if D actually was the highest probability word, maybe it could not have the highest probability. But they all are accounted for in the loss, right? Cross entropy loss. So it's the negative log of the probability of the true label. As long as I still assign quick to be a reasonably high enough probability, I'll not suffer too much loss. But yeah, for each input word, I'm getting a distribution over all the words in my vocabulary, and so in that distribution, I want at least these words to have high enough probability, so I won't incur too much loss. Yeah, so this slide is just kind of setting some numbers. Okay, let's say we have 10,000 words in the vocabulary. Then the input word is for simplicity, how do we even input the word? That's where the word to, that's where the embedding has, we need to figure out the W matrix. So for now, since we don't have an embedding yet, when we want to pass the word brown, we just pass its index basically, or in some sense, where does the brown word occur in the dictionary? Maybe it's maybe it's the 100th word. Then we pass the number 100, or we create a 100 coordinate vector where 100 coordinate is 1. It's essentially the same thing. Okay. The true label is also 10,000 dimensional because that's the dimension of our vocabulary in this slide. And what does the network do? It's a classification network, simple three-power network. So clearly, it's going to also generate 10,000 scores, which will be transformed to probabilities, right? So this is just the kind of just putting some numbers. Okay, if we restrict our vocabulary size to 10,000, this is how numbers will look like. And let's actually look at the network. So what's going on? So I think we're talking about ads now. So yeah, let's say ants was predicting something. Okay, this is a little different example from the brown word, but let's say it's ants or brown, doesn't matter. Actually, this is like completely illustrated. So let's say it's still brown, but there's some location where you'll set the word one. Sorry, you'll set the coordinate one. Okay, and so this is my 10,000 dimension vector. That's the input. Okay, here there is no semantic stuff. There is no embedding going on. There is no embedding here yet, and we want to get an embedding. And we said we'll only pick a 2-layer neural network or one hidden layer neural network. So we'll just do a transformation from here to some intermediate values, the activations of this first layer. And then from here, I will not even do anything more. I'll just try to get a 10,000 dimensional score vector. Okay, so there's one matrix here and another matrix here. Okay, and there's also going to be biases if you want to add bias. Interesting thing is in this word-to-vec network that they propose, they did not even put a nonlinearity in the hidden layer. Okay, no nonlinearity. So you may say, okay, effectively, if you don't put nonlinearity, then it's like literally saying there's one transformation from there to there. That is true, okay, in theory, but if you don't put nonlinearity and still have matrices multiplying each other, then the dynamics of optimization is still, it's a search space where it doesn't. It still has the complexity issues. Okay, it still has the optimization issues. Okay, because you're now talking about products of parameters instead of just a linear transformation. Just all I'm trying to say is that you could map this back to a simple logic regression setting, and that optimization problem we know is nice. It's very robust, and so you can easily get to the single optima. But if you have a sequence of matrices, they're all multiplying each other without nonlinearities. Although they can effectively replace with a linear transformation, but if you just leave it as product of matrices and try to optimize, that's still a messy, hard problem because there's a bunch of products going on. Okay. So this picture, and we'll probably come back to this picture, is already shows you the vision of why the simple network can capture that distributional hypothesis that we want to capture. That words that appear in similar contexts hopefully have similar vector embedded. Okay. So let's actually spend some time on what the embeddings are because I didn't show the matrix. Let's skip the objective. I don't want to talk too much about it. It's just the I didn't put the negative sign. If you put the negative sign, it's just a cross entropy. It's the prediction of the nearby word given the current word. Okay. If you're going to consider all nearby words, then that's why I'm doing a sum over a previous two words and the next two words. Okay. The objective is just cross entropy loss. It's just a regular classification problem. So, what are the embeddings now in this network? Remember that we have a weight matrix. Let's call it W0, the first weight matrix. Then the first hidden vector or the activation vector. I'm just taking the transpose of it. If you don't take the transpose, it's W0 times X. Okay. Plus B is I'm ignoring the bias. H is equal to W0 times X, right? Or H transpose is X transpose times W0 transpose. Okay. Or let's call this W0 transpose W. Okay. This is just a simple, I'm just redefining W0 transpose to be W, nothing else. That's just so that I can interpret the rows of W to be word vectors instead of columns of W0 to be word vectors. That's all. Okay. So the first transformation is nothing but you're getting an input X. You're getting an input X at one hot encode vector. You're just transposing it, multiplying with the W matrix, and you get some hidden vector out of it. Okay. The number of I just did this only because so that I can I can have a nice shape for W instead of W not having like the opposite shape. So W will have 10,000 rows, and number of columns of W you get to choose. Let's say we chose 300. Okay, the word2vec folks chose 300 as one of the choices. Okay, why 300? Why not 30? You can choose 30. You can choose 3,000. It's up to you. Okay. So so the first transformation, that W matrix, the transpose of it, of the W matrix, we're just calling it as the embedding matrix. Okay, and so every row of that matrix essentially what we are defining, we're just redefining to be the word vector for each of those words. Okay, why is there's one row per word and each row has 300 numbers in it, and so we're just defining that to be the word embedding for that word. Okay, so this is what we wanted to learn, actually, the W matrix, right? The auxiliary task about predicting a neighborhood word and all that is just a means to this end, which is to get a word embedding. And this thing on the right is our word, the W matrix. Okay, I mean it's the same thing on the left, except on the left you can think of this, the left side is W naught transpose, and one on the right is actually each row is actually 300 length or 300 columns and 10,000 rows. So that's actually our W matrix. Okay, so that hidden weight matrix, the first weight matrix, I'm just reinterpreting the transpose of it to be a matrix where every row corresponds to a word embedding. That's all. Okay, so what is happening with the first step, right? So when we multiply the 10,000 dimensional one hot encoding, let's say the brown is some 1 and everything else is 0. When we multiply it with the word this W matrix, what's happening is that one hot encoded vector, actually there's a picture, yeah, that one hot encoded vector, we transpose it and we multiply with the matrix. This type of vector, when it multiplies with the matrix, all it does is pick up a row. That is easy to see that. All it does is pick up a row. And so basically it's like indexing. Okay, what was the input word? Brown. Let's just index where the brown's word index is or the row is. Just that's the vector to be passed on to the future, to the next layer. Okay. So yeah. So here I'm just showing the full transformation. I don't think it's needed because we have seen this transformation again. So let's actually look at the intuition. Okay. So this is actually the most important slide, not the previous slide is showing something, but that operation we already know. So why are we getting vectors to have a reasonably, why are the representations of these vectors in this auxiliary classification task that we design? Why do they have similar vectors for words that appear in similar contexts? Okay, that's because if two different words, let's say word 1 and word 2, have similar contexts, and this comes back to our previous discussion also, that if they have similar context, that means words that are likely to appear around them are going to be similar, right? So brown will have a bunch of words and red will also have similar words. Okay? Not all, doesn't have to be the same, but kind of similar words. Then the output probability vectors or the output probability scores or the output probability distribution should look similar. Okay, red and brown should have almost the same probability distribution profile, probability mass function profile. Okay. Now you can reason back from there that hey, if the output vectors are similar, right? If the output vectors are similar, but the output vectors is just a linear transformation of something that was produced at the hidden layer, right? The output vectors should be similar for two words. That means that the hidden layer should be similar because it's a linear transformation. Okay, linear transformation doesn't. If two things are similar or nearby, linear transformation doesn't expand or contract or change the similarity aspect. Okay, I mean, it scales and does everything uniformly for all the points. Okay? Linear transformations, right? That means the hidden vectors should be similar for these two words. If the hidden vectors are similar, that means that the hidden vectors are nothing but the actual word embeddings themselves. That's what we saw in the previous slide when we were doing a lookup of an index. That was literally we were picking up a row, and that was actually the hidden vector. So it's very, it's actually nothing deep going on. All I'm saying is two words have similar context, they should have similar probability profiles. If they have similar probability profiles, because we're just doing a linear transformation, the hidden vectors should be similar, and hidden vectors are nothing but exactly the row vectors, those rows of the embedding matrix. And so therefore they're supposed to be similar. Okay. I mean, there are many ways to say the same thing, and we had a discussion earlier. It was the same idea. Okay.
What's the definition of similar?
Similar, you can think of in terms of cosine similarity. You can think in terms of Euclidean distance, whatever you want to. Yeah, all these definitions are. I mean, this again a design choice of what is similar. So, like I think in the previous lecture we saw similar embeddings for similar words. Like if the word France, what are the other words near to it? They're actually just Euclidean distance. Okay, like we projected words down to 2 dimensions. You could see that the days of the week were all close to each other. You could just think of it in terms of Euclidean distance. You could also think in terms of cosine similarity, because these words you have to have an origin to talk about cosine similarity, right? So these words have, the angle doesn't change much. They're all in the same space, same area, so the angle doesn't change much. So you can think of them as similar one. Okay, so there's actually a lot of practical concerns with this approach, in the sense that this is doing a number of, the number of classes in this classification is just too many. It's not 10,000 words, right? How many words are there in English dictionary? Does anybody know? 50,000, 100,000, 500,000, something in that scale, right? So, and so the number of parameters is just too many, and these are even the embedding matrix. If you have 50,000 times 300, it's a large number, right? It's already going into some tens of millions. Yeah. So at least at that time, you needed some intelligent way to kind of deal with backpropping through and updating all these huge number of numbers every time for every batch. So there were some ideas. I'm gonna skip them. Some ideas that we can look up in that paper. It's a useful paper to read, because they wrote it when they didn't know much about much about what all deep learning has done now. So it's a good perspective to get a sense of what they were thinking of when they wrote that paper. I think that's the paper at the bottom. Let me skip those ideas. They do some selective updating of some weights only and so on. Okay. Yeah, and they do many other things that we're not going to talk about. Like they actually merge multiple words and call them a new unique word for getting embeddings and so on. Let's actually skip that. So some version of Jensen. I don't know if Jensen is currently still has this, but so there are some popular packages in Python, Jensen, Spacey being a couple of them, and so you can, and obviously Tosh Text also. So they have just like Tosh Vision, you can also download models, pre-trained models. So Jensen, for example, is how you download a zip file from Google, which would have the embedding, and then you just load it as a model. And you can call, okay, what's the most similar words to the word good? You have these are the words that are similar to the word good. Obviously, not everything is a synonym, right? So you can see that terrific, bad, lousy, they're also similar because they appear in similar contexts. Okay. So but these are all the vector representation of the word good is a 3-dimensional vector, and there is now these words are now capturing word-word relationships, some semantic similarity between words. Okay. So wherever you're doing one-hot encoding, you can just use a lookup and use these embeddings instead, actually. Just like fixed feature extraction of the CNN model, like a ResNet 18 that you could use for any other, as long as they're somewhat similar domains, you could do that. Okay. Any questions about this? So it's a at least fixed static embeddings. That's what we discuss currently. We'll see conduction embeddings next lecture, but it's worth playing around with it. Also, just doing nearest neighbor search. Then once you have vectors, you can do many simpler things that you would do for tabular data exploration. You could do that here, and that's where I think some of the slides that I skipped. For example, let me go back to one of the slides. I'll skip these because there are some extensions to embeddings. But for example, some paper from actually around 2013 itself, maybe not the word-to-vec model, but some other model. They were trying to say that, okay, there's actually some other side effects, like if you take the difference between words, the other vectors, right? So words are vectors, so the difference between words is all the vectors. So if you take the difference between woman and a man in terms of a vector, that vector is similar, again, maybe directionality, maybe the length, whatever it is, to a difference between orange and uncle. Some side effect. or side effect or something that reinforces, actually, I think that's the only one I have, but yeah, here you can see France minus Paris plus Rome is approximately equal to Italy is some side effect. Okay, so actually let's then switch to the new topic. Again, the goal here is to, for the new topic is to, I don't know, did you guys do any time series analysis in any, did you do a full course in time series analysis? One. Oh, okay. So anybody else has worked with time series models before? Have you heard of ARIMA, or moving average, autoregressive models? No? So language models like the Markov model and stuff that we saw, or in general, many language models are generally autoregressive in the sense that you can think of it's like a time series, a bunch of numbers like stock prices and so on. Your next prediction depends on the previous realizations of the or previous parts of that sequence. Okay. It's just so whatever we see today can be used for time series models, just like much of machine learning can be used for time series situations without even thinking about too much about time series also. Okay, that's something that people miss, that time series models, the time series situations or time series problems doesn't mean you need to come up with another set of very different models. You can just use random forests or gradient boosted trees or anything else also for time series. It's just that you have to think through how do I map the time series problem to your to the problem at hand. Okay, and obviously the types of guarantees that let's say ARIMA models and so on will give you, you obviously might not get most likely if you just use a machine learning model, but you will be able to predict, you'll be able to predict the next element of the time series. Okay, and so today's models also we'll see can be used for time series. In fact, a lot of people try to do that for their projects, but let's see. So what's the outline? We'll look at the general definition of recurrent neural network and also motivate like what applications kind of need this type of model. So in terms of models, we've seen feedforward, CNNs. We saw word embeddings, which are not really models, but like embeddings like image embeddings. And then we're going to see the fourth category. This is the canonical model for sequence-to-sequence modeling. Okay, and then next lecture we'll see a more enhanced version, which is actually the backbone for all these large language models, called the transformer architecture. Okay. So today's objective: general introduction to sequence-to-sequence modeling and RNNs, and then a specific instantiation called the long short-term memory architecture. Okay, LSTM model. And we'll just look at the forward pass, and you'll see that in hindsight we are interpreting a lot of things, but it's just a neural network. Okay, so it works well, and we can interpret how it's laid out using some intuition, and I'll discuss that intuition. Okay, you can take it or you can ignore it if you want. Okay, so let's look at the applications. But what type of applications need this new category of models, right? So far we have been looking at this extreme left. Okay, just classifier with a fixed input length and a fixed output length. When I say fixed input, I'm thinking of fixed feature vector. So if my table, let's say I'm doing tabular data and I'm building say P4 neural network, my input is of same, is of a fixed size. It could be 10 dimensional, it could be 100 dimensional. It's not going to change, right? So as I process my data, it's not going to change. Similarly, the output. Let's say I have 10 classes, then it's just 10 classes, 10 scores every time. It's not going to change. Okay, that's what we've been looking at so far. And all these examples to the right of it are all situations where you might have to generate variable length output, or you might have to consume or take as an input a variable length input. Okay, and of course you can mix and match them. So here you're taking a fixed length input and producing a variable length output. So this is, for example, image captioning, going from an image to text, which is the opposite of DALL-E, but it's the same idea. Or you can do the opposite. You can go from a sequence of inputs to an output, which is, I guess, generative AI is an example here. All I have written sentiment analysis as an example. So you can take a prompt and you can generate an image, right? So that could be one of these variable length input and single output. Or you can do combinations, right? You can have variable length input and a variable length output, whereas where you only want to generate the output after you've seen the full input. Or you can do variable length input and variable length output, where you start generating output the moment you see the first thing. It's just it all depends on what application you have, and all these we still are in the supervised learning setting, which means that we do need pairs of annotated data. So, for example, image captioning, we do need images and their captions, a bunch of them, so that we can train such a model. Okay. Yeah. So you saw some blocks and some arrows. These arrows are trying to capture some idea of persistence. Okay, this is exactly something that time series models also you want to capture, which is the idea of what happened before. Okay, what happened with the previous input? Like when you're trying to predict, let's say, one output here, not just depending on the current input, but also, okay, what was some transformation of what the previous one, some transformation of what the previous thing happened. Okay, so the idea of persistence is what we want to capture. Naively, P-power networks and CNNs, at least naively, that the way we discuss it, they don't capture that persistence, right? So you would do classification on every frame of an image, but you're not recollecting what classification and what was the input last time, for example, right? So that's what we want to capture. We want to persist some information that happened before. So we're going to be auto-regressive. We want to know what happened before in terms of output, or what happened before in terms of input also. Okay, so recurrent neural networks are capturing this idea of persistence explicitly. So the way they are represented is actually using a box, a block, or a computational box that is reused again and again. So that's why the word recurrent. So let's say this box A or block A represents some computation, a base network. A base network just means a fixed computation, some fixed input, fixed output computation. It's just that if this network has two inputs and two outputs, then you can see that you can actually reapply it again and again and again. Okay? So, for example, for the current input, you can generate some current output like a hidden vector. But since you are also generating a second output, you can actually use the second output the next time you're calling this block. Okay, so now the next time you call the block, there's a new input and whatever was computed previously as well as input. Okay, so this is one way to represent an RNN, but it's actually simpler probably to represent it this way, which is you have a sequence of inputs, and each input could produce something. I'm using the word letter H to represent that they could be hidden vectors. It's just that they themselves may be useful for your prediction. Maybe you take these hidden vectors, do some linear transformation, get score vectors, and maybe do classification immediately. But you can use them, you need not use them. But basically, this X0 gets transformed, and this block is also producing something that can be consumed by the same block again in the future. So it's like two inputs to this function and two outputs to this function. Okay. Yeah. So the sequence repetitive nature, it can work with words, it can work with images, right? So we just saw how to work with words. We have word embedding, so you can just think of passing word embeddings instead of one-hot encoding or some other variation of this word sequence. If you want to maintain actually the sequence nature, the sentence has a sentence generally has word in a particular order, right? So if you want to maintain that order, it's very easy to do so. You can just look up what the embeddings are and then just pass the embedding one after the other to this type of an architecture. Okay. And so here, I think you can easily see how you can do sentiment classification or sentiment analysis, right? You can pass the movie review, each word of the movie review or something like that, product review. And then at the end, when you pass the last embedding of whatever the last word is, then you see, okay, what's the hidden vector? Maybe that you try to transform into a score between a positive review and a negative review, for example. So these are called unrolled diagrams, I guess, in comparison to this one, which is just showing the same thing but with a arrow, circular arrow like that. Yeah. Important thing in this slide is that all these blocks in this family, at least the model I'm discussing right now, they all have the same parameter. Okay. So when you think of backprop, let's say this led to some prediction, and maybe that led to some loss. I mean, it's a given example. then that loss, when you do a back prop, you're actually finding the grade of the loss with respect to, parameter theta. Then parameter theta is part of, is appearing here, but is also appearing here, here. So there's going to be some aggregation of gradients. Okay, so at the end of the day, you want to find the gradient of the loss with respect to just parameter theta, not the parameter theta. You don't want multiple gradients. So you have to, you basically add them together. Okay. So let me take some notation. So it's going to be useful to open that box A. Basically, so far I've been showing some green box A with the letter A with some parameter theta. We're going to just open it up for the base vanilla RNN. Okay. So for that, we're going to represent yellow boxes to represent a neural network layer. Okay, think of it as a feed forward layer. Sorry. And then this means a vector is going from whatever left to right. This means two vectors are getting concatenated, one below the other. Okay, and this means the same vector is getting copied or is being input to two different locations. Okay, this is just a notation that we want to introduce. And with that, here's the opening up of that RNN box. Okay, so this was the A, right? Same A now enlarged. Again, also curved the borders. But this A, this is how, at least for the vanilla RNN, this is how it looks. Okay, so you have an input, two inputs coming in. Now they're merging together, which means that they're getting concatenated. Okay, so the previous HT minus one, in that case, you can see that it's producing HT, and the same HT is being passed to the next cell. So that means that this thing that's coming out is actually HT minus one. Okay, so HT minus one gets concatenated with XT, and then it passes through a feed forward layer. Okay, and tanh over there means the nonlinearity is a tanh nonlinearity. Okay, a feed forward layer just means a linear transformation Wx plus b, and apply tanh nonlinearity, and then that's your output. Okay, so it's a very, very simple block. Okay, it just has essentially one weight matrix. Okay, and maybe you can add a bias also there, and that's it. And there's nothing else to tune, right? So just the weight matrix basically, and the bias vector. Any questions here? Okay, so here's with just NumPy, just to show. I mean, I know you've already done a more complex problem in your assignment, but just to see how it's defined, it's just NumPy. I mean, obviously, torch implementation is different, but in NumPy, you can start with initializing for three fields, right? So three attributes. So H, W, and bias. H is going to be things that we keep changing. Okay, H is going to be, we need to remember the previous hidden vector that was generated so that we can use it, right? And W and bias are the two parameters of this RNN block. Okay, and when we take a step, which means that we get an XT, okay, we just take what we remembered from last time, self.h. You do a horizontal stack with XT, okay, and then you do an NP dot, or there are many ways to represent this. W times that concatenated vector plus the bias parameter. Okay, and that's it. And then you apply tanh activation. So this is actually very straightforward. And then you're actually saving that, you're rewriting the self.h with that new vector that you computed, and then you're returning whatever the self.h was also. Okay, and so if you have a for loop with, let's say, 5 steps, we're just generating some random vectors, random vector of length 4, then that's the XT, do a step, XT is passed in, you get a HT, just remembering HT, but you do that in loop. Okay, this is just trying to show you how an RNN you would write if you write it just a forward pass this way. Okay. Any questions here? And this 3 and 4 are just the parameters of how much is the dimensionality of your hidden vector and how much is the dimensionality of your input. Okay. This 4 is the same as this 4 that I'm generating, the 4-dimensional vector I'm generating. Any questions here? Okay, so yeah. Yeah, the bottom line is just illustrating, okay, if you define the RNN block this way, I'm instantiating an object from this class. With 3 and 4 means the hidden vector will have dimension 3 and the input will be of dimension 4. And I'm just saying for I in range, I mean, you can put I if you want. I mean, we're not using the variable, that's why we're using the convention underscore to ignore the variable. For I in range 5 means, take 4 steps. I'm just randomly generating a vector here and p dot random of dimension 4 because we want to create an input of dimension 4. And I'm just passing it as an input while calling the step function. The step function is an input, and then it's computing is doing these 2 steps and returning the hidden vector, and that's what I'm printing here. It's just if I had created a class like this, how do I use it to do a forward pass? So let's actually cover this example and then take a break. So this is an example of let's build a simple language model. Okay, we saw a simple language model when we looked at the Marco language model last lecture. So this time we're gonna just change the same thing, but now use an RNN. We'll still keep the language model at the character level, okay, just to kind of have that 2 examples. And in fact, this is going to be part of your assignment 3 question 1 also. So what do you want to do? We want to build a language model given a large amount of text. Okay. So what we want to do is actually to model the probability of the next character given a sequence of previous characters. Okay. So this is going to be different from the Markov model. Markov model, we had to fix the order. We have to choose some order, like the order 2. Then given the previous 2 characters, we were remembering how many times which character appears, some sort of conditional probability mass function. And then that's essentially our Markov model. Like given 2 characters, you would say the 3rd character. Then given the next 2 characters, you can generate the 3rd character and so on. Okay. So here it's a little bit different. What we want is, given a variable length of previous characters, we want to say what is the distribution over the next character. Okay. So it's richer. Okay. Application of a language model, like as we know before, is generally to generate new text. And you can also do all sorts of things. If you know how to generate text, that means it's a generative model. If it's a generative model, you can also do other things, like you can do predictions, and you can do predictions instead of just generation. Yeah. So we'll stick with just one example. So let's say our vocabulary is just 4 letters, HELO. And in fact, our training example is just HELLO. Okay, so just as an example. Then if this was my training data, this was all my training data, or one training example, then from this example I can create 4 input output pairs, right? Very similar to our quick brown box example. So given H, I want to predict E. Given HE, I want to predict L. Given HEL, I want to predict the next L. And given the first 4 letters, I want to predict the last letter. Okay, so those are my input output pairs. So you can imagine if I have a network, if I input a embedding of the character H, I want to get a distribution over. I only have 4 letters in my vocabulary, so I have a 4-class classification. I just want the coordinate, whichever corresponds to E, the second coordinate, to be high. Okay. Similarly, when I pass in these 2 embeddings, one after the other, then I want to have the L coordinate, the 3rd coordinate, to be high. Okay. So for simplicity, let's say we embed let's say we have an embedding for each character, which is also 4-dimensional. Doesn't have to be 4. I mean, if you make it 4, it's like one hot encoding, essentially. But it could be 3 or it could be something else. Okay. So here's the kind of illustration of what's going on. So input characters are H, E, L, and L. So in the previous slide, I showed you 4 potential examples that you could have created, right? So H leads to E, and HE leads to L, and so on. But we could actually work with all 4 examples together at the same time. Okay. What do I mean by that? So we can say, given a 5-letter word, we can take the first 4 letters and give them as inputs. Okay. And we can take the second word to the last word, second character to the last character, and use them as output, ELLO. Okay. And what we're trying to say is that H, for example, this is the one hot encoding for H, let's say, leads to some hidden vector. Remember the A block was producing 2 numbers. In fact, if you open it up for the vanilla RNN, it was just producing 1 hidden vector. It produced some hidden vector and then some transformation back to the 4-dimensional space. Let's say the hidden vector is only 3-dimensional. You have to project it back to the 4-dimensional space, but it's not really projection. You have to transform it back to the 4-dimensional space. And you got 4-dimensional scores, and then you're just checking whether the second coordinate for E is high enough or not. Okay, if it's high enough, then your cross entropy loss for H as an input, E as an output is going to be low. Okay. Similarly, but at the same time, whatever we generated here can be used for the next RNN call because we got the new input E and the previous input H together inform us to make the next prediction, and we want in the next prediction the index for L to be high value. I mean, currently it's not high; it's the lowest in fact, but we want to tune the parameters of this, which is the W matrix, such that this number becomes higher than the other numbers. Okay, so you can actually use, although I said you can do 4 different examples. H leading to E is one example, and HE leading to L is a separate example. But we can actually think of all of them as like one input output pair, where the input is first word to n-1 word, first letter to n-1 letter, and the output is second letter to nth letter. You can consider them simultaneously if you want. Okay. Any questions about this diagram? And ignore the numbers. The numbers are like just to show you that okay, there are some vectors here. Okay. Yeah, the loss is going to be still cross entropy loss. So now in the previous slide you saw that you'll have 4 cross entropy terms for this input output pair. Okay, this collection of letters and collection of letters that are being predicted. Okay. So here's like why do we need an RNN is, in this illustration is because when the first time we see L, the next character should be L, but this, the second time we see L, the next character should be O, which means that there should be some information about the previous thing that happened that you need to retain. Okay. Obviously, if you had just a 2 order Markov, that would still work. I mean, it will still, do this distinction. But if you had only a first order Markov, then given L, it's unclear whether it should produce an L or an O, right? So just to give you an illustrative example. Okay, so any questions here with just the introduction to sequence modeling? It's a different class because your input and output lengths are not lengths, but sequence lengths are not the same. So that's actually interesting. It's something that first time you say it is like, how do you even work with this type of problem, right? How do you even represent the input data? The best way to think of it is like sentences and so on, which are going to be variable length, and still want to make let's say some sentence classification type of situation, right? And this equally applies to all whatever we discussed so far. Also applies to time series data, right? Even if the data is numeric, it doesn't have to be vector embeddings and all that. You can still do next whatever, some forecasting, some reference, some future event prediction. Okay. It could be the next stock price, or it could be something that happened 30 days later, whatever it is. Whatever the target, you can predict. So let's take a break for 10 minutes. Maybe actually 14 minutes, and resume at 5:10. Yeah.
Have like
More than one word? Yeah, I mean, this illustration was just our vocabulary size only had like these, these letters. But if you had 26 characters, and if you had multiple words, then there would be different examples in your data set, right?
Would it be like how many?
So let's say you have a data set of paragraphs or sentences. Okay? You ignore the sentences completely, just break them into a collection of words. Okay? And each word is now for me an input output pair, where the first to last but 1 characters are inputs, and the second character to the last character outputs. So I need to train these parameters of the RNN, the yellow block that you saw. Keep training them, keep changing the numbers so that they can, these HELL produces ELLO, and maybe some other word, let's say input INTU produces NTUT, right?
So if my paragraph has like 50 words.
Yeah, all of them are 50. So it's the same network, but you have 50 inputs and 50 outputs. You have 50 words, right? So the first word would be HELL and then producing ELLO. That's for just the first word. The second word, let's say input. The first 4 characters of input would be the input, and then the NTUT would be the output. And let's say that there's one more third word figure, then FIGUR would be the input, and then IGURE would be the output, and so on. And they could be variable length, right? So it doesn't have a 4 length. It could be whatever is the length of the word.
How many, well, my question is like, how many, the hidden layers, like sets of it are there? Would that be like?
So there could be so the number of hidden outputs that you can generate is just dependent on what's the input length. Where input length could be variable. So this 5-letter word had the input length 4. A 10-letter word, if there's some example coming up later, that will have that will lead to producing 9, right? So 9 hidden vectors, but it's all produced by the same block with the same parameters.
Oh, okay.
Yeah. So it's the same parameters. It's not like we are learning a model with, like multiple parameters. It's just the same parameter, right? So the only thing we're training is the weight and bias of this matrix here, irrespective of how many, whether it was a 3 or whether it's a 5 or whether it's a 10. 10 times we are reusing that block. Okay, let's resume at 5:10. Okay, before we move to the LSTM architecture, as I said, in the LSTM case, we're going to just do a forward pass. And there's going to be some interpretability, but it's mostly just to kind of appreciate the architecture. It's going to be more involved than the RNN architecture that we just saw, with just one TANH feed-forward layer. So it's going to have a few more things. But before we move on to that, I wanted to show you it's a good practice to actually, given that you finished assignment 2, to start really relying on the PyTorch documentation. Obviously, you can rely on examples from other sources, Stack Overflow and stuff, but it's good to also read the documentation. And if you really want to do it, more justice, you can look at the PyTorch's open source repository. Okay, it really gives you what's behind the scenes in all these function calls, right? Obviously, it has a lot more complexity. It's not like a first time. It's not a small code base, right? There's like, I don't know how many, 50% is Python and actually 42% is C++. And that's what actually makes it fast, right? So Python is a slow single-threaded language by default. But let's look at this RNN description, because it's a little bit different from the NumPy description that we just saw. But it's worth. I want to point out a couple of things so that before we get to assignment 3, you notice these things and at least know that could be source of errors. Okay. So firstly, the RNN definition is the same as what we did, except they, instead of concatenating and just calling a single W, they said, okay, let's not concatenate. If you don't concatenate, then it's like saying, okay, this vector multiplies with a W matrix and this other vector multiplies with another W matrix. Okay, you can actually break down. If you have a long vector, if you break it down into 2 separate vectors, then you can actually break down your wide matrix into 2 short matrices. The left side of the matrix will multiply the top vector, and the right side of the matrix will multiply the bottom vector. Okay, that's the way they've written it, and also transpose it for some reason, but that's the operation that's going on in each RNN step. Okay, so actually, yeah, so that's what's going on in RNN step. In fact, let me just mention nonetheless. So what's the difference between this RNN cell and RNN is that RNN itself will take care of your for loop, in the sense that if you pass a variable, let's say you pass a 5-length input, then it's going to produce those 5 hidden vectors. Okay, so you don't have to take the first hidden output H1 and then pass it to second RNN call and then do that. So as long as you give the some length input, like say 5-length input, then it'll take care of, okay, let's pass the first hidden output to the next next time I call the same the A block basically and do that. Okay, so RNN cell on the other hand just does that one step. So you could just do you can call the RNN cell 5 times by wiring up the way we did it we just saw in the NumPy 5 times, and it's exactly the same as the RNN block, the RNN, okay, block. So, but let's directly look at the RNN because it has a couple of, let me just close this, couple of interesting things. You can change the nonlinearity to ReLU. By default, it's Danish. So people are asking why, why we're even studying about other nonlinearities is because by default, RNNs have Danish and nonlinearity. Okay, you may say, okay, why not default it to ReLU? Is because maybe Danish works better, right? So in the types of applications that they've seen so far. So what I'm trying to say is that the moment you have deep networks, it's not like one function uniformly dominates another function everywhere. Okay. So when I say that, I just mean in terms of performance or something like that. It's not the case, and so really it's a case by case basis. Now, they have some extra things like number of layers, which we have not talked about because we only had that a block with just one yellow thing. You can actually stack them. You can stack an RNN block on top of another RNN block, and so that the H that you produced goes as x to the next RNN block if you want. Okay, so that's like a stacked RNN. We'll briefly talk about it in the slide later. So for us, it's, let's say it's 1, default is 1, and so let's ignore this. Yeah, and one of the important things is also this setting. Okay, so the bias and nonlinearity, it's okay, we can choose something. Important thing is batch first. Okay, batch first is the notion that if you have a batch, Torch, I don't know if you've seen it already when you were working with CIFAR 10, but Torch assumes kind of expects, or at least it's important for at least these RNN type of models. The batch index is the second index. Okay, that's not the intuitive thing to think about, but batch index by default is second index, unless you explicitly say batch index is the first index, therefore you need to set this to false. Okay, this is where people get confused with respect to the dimensions of the matrix, dimensions of the tensors they're producing. Okay, so if batch first is true, then the first index will be a batch index, which means that if you have a batch size of 256, then the first coordinate, if you index 1 to whatever 0, 1, 2 to 255, that will pick that batch example in that batch, okay, first index. The second index corresponds to the sequence length. So if all our sequence inputs are of exactly the same word length, which is, let's say, 5 characters, then there's going to be 5, right? And feature is the number of features, number of coordinates in that xt and xt plus 1 and so on. So for example, if there's a word embedding and let's say it's 300 dimension, then this feature is 300 dimension. Okay, it's just a feature vector representation. Feature vector length. Okay, but by default it's false. Okay, so when you use RNN block, this batch first is false, which means that it is expecting this type of a tensor, not the batch. So the batch index is the second index. Okay, just be careful about that. Why did they choose design choice? It's not to make make people confused or anything. It's just this, I guess, probably helps them with the computation behind the scenes. Okay? And let's also ignore dropout. We have already discussed dropout. You can actually easily add dropout by just setting dropout is equal to 0.6 or 0.4 or whatever you want. And finally, there's also something called bidirectionality. We'll visit that when we talk about number of layers. Okay, we'll think about that later. So so it's a very good exercise to go through this page. For example, look at this legend here. N is the batch size, and therefore, if input is batched, N is in the second index. Okay, the batch is in the second index. The sequence N is first index. Okay. Whereas if you set batch first is equal to when you set batch first is equal to true, which is not the default, then you can set your batch index to be the first index. Just remember that. Yeah, it's a nice documentation, and obviously, if you want to check everything, you can go to the PyTorch repository and actually look at the implementations. Okay, so which I guess you can go into Torch, and much of the functions are not, it's going to be C++ based, but you can look at some parts which are Python based. Okay, like torch.nn, right? We were looking at backends parallel. Okay, let's see what's going on in it. Okay, init is not doing much. utils has some py files that you can look at. RNN, there's RNN here, but it's actually some helper functions rather than the RNN class itself. But you can get a sense of like what's going on by going through this code. It's not. It's actually, you can see that there's a monumental effort that went into writing just this package. Okay, there's like so many function calls, so many function definitions here, everywhere, and you have all the other softwares which also have similar amount of complexity. So, but it's good, we need to stand on the shoulders of giants. So they've already written this lower level things to deal with gradients and everything in an error-free way. So you can focus on, creative parts and build interesting applications. Okay, so let's then come back to LSTM and basically look at, basically do a forward pass. So I think we discussed why we're looking at RNN is because we want to have some persistence. Okay, so hopefully the x0 that was passed in, maybe when we're looking at processing x10, and maybe x10 was the last input and we want to make, say, sentiment classification, we hope that x0 is somehow also captured because we have all these connections, right? That's the thing, but that's what we want to do, and that's why we started using RNN. But the question is, can they persist information which is right before the output or long time ago? So can they persist both sets of information easily? And the answer is it depends, right? So for example, if you use the word advanced prediction, maybe you can say models because only the first, most recent words are kind of useful. But if you had a huge, text sequence of words where you set UIC and then later you're trying to predict the word, and if it needs to be Chicago, then the indicators of being in Chicago, like UIC or some other information, if they're far away, then does it really capture that? Okay, that's an experimental observation you need to make. And sorry, let me get rid of this. And it turns out that RNNs are not by default that good at doing this. So the case here was like where you're, let's say this was being used to produce the current output. And if there are things very close by, like maybe not immediately close by, but let's say one step away, you can still use it. But if the information that is relevant to kind of the answer that you're producing at this point, then can RNN deal with it? At least the RNN that we saw so far is not able to do it. So what we're going to do is just change this A block to some other block, let's say B or A prime or whatever, and that block is just an LSTM block. Okay, so it's just a plug-in replacement for wherever you're using the RNN cell or whatever, you're going to just change it to an LSTM cell. Okay, so that's what this says. LSTM have some history from I guess 1990s, 1989. And they just the original authors termed it as long short-term memory cells. Okay, but there is no memory component; it's just a pure computation. And just like our vanilla RNN cell is just two inputs, just a linear layer and some nonlinearity, and then two outputs. Here also, there's no explicit memory or some RAM or something. There's nothing else going on. It's just some computation. Okay. Yeah, so let's see how they work. So this is how the LSTM architecture looks like. So the A block, so wherever you see an RNN cell or an RNN instantiated in Torch, you can always replace it with LSTM. And it's just literally find and replace the word. But what's going on in that cell, has a few more moving components. So if you remember our notation, yellow blocks represented something to do with the feed-forward layer type of thing. So you can see that there are 4 such yellow blocks here instead of just 1. Okay. But if you want to really map it back to the vanilla RNN that we saw, this is actually the original damage layer. But we have some extra layers to kind of modulate information, change some coordinates of the output vector. So further, also there's now instead of 2 inputs and 2 outputs, there's looks like there are 3 outputs. 1, 2, and 3. In fact, very similar. Although there are 3 outputs, one of the output is just the same. Okay. So let's actually briefly talk about what this. So what's going on inside this A block? Okay. So we are now zooming into the nitty-gritty details, but don't lose sight of the overall picture. It's just we want to work with sequence data, and as long as you appreciate how RNNs work, vanilla RNN works, you can just plug in LSTM there as well. Okay. So notation, one extra notation. So same as before, yellow blocks are neural network layers. One extra notation is a point-wise operation. Point-wise is like element-wise multiplication or something like that. We're gonna represent it using a yellow, using a pink circle. Okay, so that's the only new notation. The other ones are just a vector, a concatenation or copy and so on. So we're gonna just think of this forward pass. I mean, we already saw the diagram. I'm just gonna explain the way you can kind of rationalize or intuit about what's going on. Is this LSTM cell has an important vector that it passes from one step to the other. One time it's computed, the next time it's computed. Let's call it steps. So the vector is called the cell state. Okay, so CT minus 1 is the cell state of the previous LSTM block, and CT is the cell state of the next LSTM block. So this kind of replaces the previous HT minus 1 as the important thing that is being passed from cell to cell. Instead, this is what we think of as like the important vector that's getting passed from one cell to the other cell. Okay, and this vector only has kind of two operations going on: element-wise multiplication and element-wise addition. Okay, so this vector, there's element-wise multiplication and element-wise addition. It seems pretty restrictive computations, but they're not, right? So element-wise multiplication. Let's say I do element-wise multiplication with all zeros, then whatever CT minus 1 was there, it's all gone. And if I do now addition, now I'm fully refreshed the vector, right? So it's a completely new vector. So it's not restrictive at all. Yeah. Yeah, I'm not showing too much. It's just these are the inputs and those are the outputs. Okay. So the cell state is where information, you can think of it. This is where the information of longer term information, shorter term information is appropriately, kind of represented. Obviously, represented through those transformations that are happening before. Okay, it's not like this is like static information or anything. This is just a vector being processed in the forward pass. But this is a vector which we think of as retaining key information. Okay. So to control that information in the cell state, the multiplication, element-wise multiplication, element-wise addition, there are going to be some things were attached, right, in that element-wise multiplication and addition. Those things are called gates. Okay. So what are gates? Gates are basically some setup using a neural network layer that can modulate information. Okay, modulate as in like because we're doing element-wise multiplication, modulate just means that we can tone down the number or increase the number. Just amplify or reduce the number. Okay. So obviously the number changes. So it's in some sense. So what we're doing is essentially like element-wise scaling. Okay. So how do we do that? So let's look at the expression. So you have a vector v, could be the cell state, and let's say we want to. There was a part where it was doing element-wise multiplication. So let's say we have a controlling vector u. Okay. Then u gets u is a vector, so it means its coordinates could be any number. So first we want to kind of put those numbers into numbers between 0 to 1. Okay, and that's why what we're doing is taking u as an input, doing a linear transformation, and then applying a sigmoid nonlinearity, and so we get numbers between 0 to 1. And if I now multiply element wise, some numbers will stay as is if those coordinates are 1. And some numbers where the sigmoid transformation leads to values like 0.5 or 0, those numbers get kind of attuned, tuned out, or maybe even 0. Okay, that's what I guess shorthand notation. When I say mathematically, it just means shorthand notation. So you have u linear transform, do a sigmoid transformation between basically crush numbers between or bring the numbers between 0 to 1, and then do an element-wise multiplication. This pink symbol earlier or this symbol is the same. Okay, that's the function. Okay, and we're going to call this a gate. Okay, it's because it's like kind of some sort of if you think of water flowing, let's say it's a vector, so there's multiple channels of water flowing, then it's basically trying to modulate how much water flows from left to right. Okay. U is some control vector. We'll see how, U will be some function of, it could be the input vector. We'll see. Actually, U is going to be some concatenation of the hidden vector from the previous cell and the input. And we'll see that actually. This here, I'm just generally describing what a gate is. And the gate appears multiple times. So this type of gate. Yeah, and there's some interpretation that we can add, but let me mention that the LSTM has 3 such gates. Okay, so you saw 3 extra yellow blocks in addition to the tannish block. Those 3 are actually just gates. Okay, so now it's like, okay, now it's clear that why there are 3 extra neural network layers. It's just all they're trying to do is essentially some sort of control. Okay? So and they're all basically trying to control the cell state. All the cell state is just one element-wise multiplication, one element-wise addition. There are like 3 gates to support it. Okay, why do we need 3 gates? We'll discuss that. Firstly, and this is interpretation. Okay, how the architecture is laid out. Firstly, we want to forget all information. Forgetting all information is achieved by the first, by the, I guess, the forget gate layer. What we do is for this forget gate, we're going to take the previous hidden vector and the xt, concatenate them, do linear transformation, and get and then apply sigma nonlinearity to get numbers between 0 to 1, and then do element-wise multiplication with the previous cell state. Okay, that's the operation going on here. So let's look at the figure. So we have xt concatenated with ht minus 1. Those two together, remember, is like the u that you were talking about. Do a linear transformation and the sigmoid nonlinearity. And now this you can element-wise multiply with the previous cell state to forget all information. So why would you forget all information? If sigma leads to values which are like some coordinates are values which are like really 0, then if you do element-wise multiplication with those zeros for those coordinates, those rows of those coordinates of that cell state vector, they are now gone. Okay, whatever information was there before. Right, and here's some example of, or if you need to remember the gender of the current subject, maybe one of the coordinates corresponds to the gender of the subject of interest right now. Maybe you switch from let's say some male to female, then you have to forget the previous gender, for example, right? So it's like just an interpretation of this thing. And again, shorthand notation, concatenation is just being shown as a comma, and then element-wise the vector matrix vector multiplication here, and then sigma transformation. That's the input. So that's the kind of gate output that's going to get multiplied to the previous cell state. Now let's talk about remembering new information. Okay, so we forgot some information. Now we want to remember new information. So for that, first of all, we remember the original vanilla RNN had the tarnished layer. That's anyway computing some new information from the current HT and XT inputs. We want to now regulate among the new information computed what is actually useful, and then add it to the cell state. Okay. So the input gate decides which values to update. Okay. From the So tarnish creates a candidate value, candidate new information, and then input gate controls, okay, among this new information that you created, which is actually useful, and then we element-wise add it to the cell state. Okay. So if you look at the operation, it's like we concatenate and do the tarnish operation just as before, but now the concatenate thing is also controlling another gate, which means I'm creating numbers between 0 to 1, and that you do element-wise multiplication with the new information, so that is the remaining information actually can get added as is with the cell state. Okay. So for example, in the new information, I don't want to remember some irrelevant information. Those coordinates will be zeroed out, for example, and then that will be added to the cell state. Okay. This is called the input gate layer. Is this layer just means this yellow blocks. Okay, there's just 3 power layers. This is the input gate layer. Any questions here? Okay, this is just interpretation of this complex architecture. Okay.
Output of the input gate layer and the output of the finger layer is the same, right?
This output and this output? They will not be all the same unless these parameters are the same.
If that's it, I mean, here.
If the parameters of these two are the same, they're not the same. Okay, each of these yellow boxes will have their own parameters.
Not necessarily function.
No, these 4 will not use the same parameters. The blocks will have the same set of parameters. Okay. Okay, I guess what I said is what's written in the sentence. I mean, there is an example like you add the gender of new subject to cell state, and maybe you previously forgotten the gender of the previous subject of interest, and now you add the new gender if you want to, and new information if you want. Okay. Then the only thing remaining is okay. Now actually forget and remember. So that's being shown. This element-wise multiplication is forgetting something, and now that we created some new information and modulated it, we are adding that back, and that's the remembering part. Okay. So I hope this part is clear with the three neural network layers. One is the TANH, and the other two are gates. The only thing remaining is the last gate, and that gate is just to get a transformation of the cell state as a hidden vector output, HT output. Why? Because HT is the one which is just a transformation of the cell state that we want to pass it out as in if it is needed to kind of produce a current output. Okay. Remember, HT can be optionally used to produce a maybe transform further to get a class probability and so on, right? So we need the HT anyway. So either you can say, okay, maybe I'll just pass the class, what is it called, the cell state itself as as an output. Instead, they decided the authors who created this cell, they decided, okay, we'll do transformation of the cell state and then pass it out. Okay. So that's the So the output is basically every cell produces an output, the HT vector. So it's a filter or transform version of the cell state. Okay. So the way it is done is first you pass the cell state through a actually it's not a TANH layer, it's the element let me just it's not a TANH layer, it's element-wise TANH operation. And then you use the last gate to figure out what exactly you want to output as well. Okay, so there's an output gate, which is again same inputs. All the gates have the same inputs, a concatenation of HT and HT-1 and XC. And these numbers are trying to figure out, okay, among the cell state, maybe some entries are not relevant for the current prediction, for example. They're getting zeroed out. Okay. And but the cell state, they're also normalizing so that the numbers are between -1 to 1 as well. Okay. So there's an element-wise TANH operation going on as well. Okay. That's it. So whatever was produced, that's the current output, which could be further transformed to, depending on the number of classes or something, and then you use that for cross entropy loss computation during training. Any questions here? Yeah.
This is just for the this part. The thing on top of TANH, it doesn't like it goes to the water part, right?
So the water, if you think of water, I mean, there's no loss of, I guess it's not conserving anything. But so this operation means the vector got copied. So this vector is going this way, the same vector is going down as well. And that vector, each coordinate of the vector is being applied. I think we are applying a TANH function. So the numbers, whether if it's a number between -∞ to infinity, it's becoming a number between -1 to 1. Okay. And that number now is getting element-wise multiplied with some number which is between 0 to 1. And that's the number that's being passed here. And this again means a copy, just like a copy here. So the same vector is being passed forward as well. Yeah, I mean, this is not complicated. We saw the vanilla RNN. It's just that there are 3 extra gates to control information because there's one more. The authors thought that this is the right kind of interpretation to have a cell state which carries long-term information. Okay, so there is an unencumbered path because previously, if you think of vanilla RNN, if there is some relevant information, it had to pass through a nonlinearity, and then that was what was passed forward. Okay. So you had to kind of so if there was some relevant information 10 steps ago, it's going to like 10 times nonlinearities. Okay. Here, if there's some relevant information, it is not essentially going to nonlinearities. Maybe it was generated through nonlinearities once, but if that coordinate is super important, maybe the sigma for that coordinate is 1 here and nothing is added here, so that information can kind of stay for a long time. Okay. You can just intuit it that way. Okay. Any questions? Here. Okay, so just to summarize, there is a forget gate, there is an input gate, which is just figuring out what relevant information you need to add to the cell state. And then here's the actual operation like element-wise multiplication to forget something, and element-wise addition to add something. And finally, some transform version of the cell state needs to be produced out currently as well as part of forward. And so for that you have output gate that just takes a transform version of cell state and element-wise multiplies, and keeps some information, zero results, and some information. Yeah. So this slide is now context switching and saying that, okay, we saw this LSTM in such gory detail, but that's not the only block that people have converged, right? So in the moment you have these building blocks, you can connect them in many ways. So there's an alternative, there's another popular, let's say, a popular block called GRU, okay, gated recurrent unit. So which was designed by some other set of folks, which have a very, very similar to vanilla RNN. They do have a Danish, I guess, block that's generally kind of present everywhere, but they got rid of the cell state from the previous architecture. I mean, so these blocks, by the way, you can also design your own block. It's just that training them and showing that they're actually better than others is going to be hard. So communities have converged to some popular templates like this, LSTM or the vanilla RNN or the GRU. Okay, I'll not discuss that in detail at all. Let's now talk about that stacking. So there was this num underscore layer is equal to 1 by default. If it was 2, then what I meant earlier was that you would just think of that as these hatches. You ignore the hatches and call them new x's. I mean, you can call them some intermediate values if you want. And these are the new hatches. So you can ignore these. I mean, although I use the same x's here, you can ignore the names here. So all we're doing is, when we get a new input, when we get an input, we're gonna first apply the RNN cell, and whatever output was there, again apply an RNN cell, a different RNN cell, and then take that as the hidden output. Okay, so you can stack. Okay, now it looks like a very complicated grid type of an architecture actually. Okay, with a lot more nonlinearities. If you're not satisfied with one nonlinearity where any of these inputs were just doing one Danish transformation and then just being produced as an output, you want people to do stacked RNNs like this. Okay, but the A can be LSTM block, it could be a regular RNN block. Yeah, I mean, they do a lot more. This comment is just saying there are other, people just iterate over this quite a bit. And, what we study, for example, in this course might become irrelevant or maybe suboptimal tomorrow also. So just don't think although we're looking at some canonical popular architectures, it's not like they cannot be dethroned by other approaches. Okay, in fact, very early versions of the course, we were only focusing on RNNs, and then the transformer architecture was released a few years ago, actually just 5 years ago, and so now we are studying transformer architecture because it really dethroned RNNs as a way to work with sequence models, sequence data. Okay, and so the most popular language models today are actually using the transformer architecture. Although RNNs also there's some some models based on RNNs that also are competitive, but not at the last last mile. Like they're not really beating the transformer ones as of today. Training, I don't want to comment too much, just backdrop, but as I said, you just need to take into account that the cells have the same parameter. Okay, and this is the full. I mean, this is just showing the same LSTM cell, but now explicitly capturing dimensionality. Okay, let's say if your input was 2 dimension, and your hidden vector is 2 dimension, and your cell state was 2 dimension, then this is how dimensions of input and outputs will look like. Okay. Any questions here? If not, I think we are towards the end. I do have one last section, but it looks like you guys are tired. The section was more about applications. Okay, so maybe I can talk about the applications because there's no. It's just like we went into the gory details of the architecture, the forward pass. Now let's just jump back 2 steps back in terms of coarseness and look at some applications that this enables. Okay, there's not going to be any more symbols and low-level details. but there will be, connections to applications that we know, right? First application is the sentence classification, which is just sentiment analysis. Like there, I don't want to draw any new picture. It's just exactly, you ignore all the previous hidden, remember if you call the RNN cell, RNN in Torch at least, it'll produce all the hidden vectors for all the inputs together. You can just ignore the first n-1 or first t-1 hidden vectors and just play with the last one to make your prediction, your two-class classification, for example. So here's a second interesting application, which is the image captioning. This is the opposite of, I guess, generative AI, the DALI 3 or DALI 2 type of thing, where we want to give an image as an input, and we just want to generate a sequence of words as an output. Okay. So how do you do that? All you need to do is somehow take the starting point as a special case. Remember, the RNNs are anyway, you can do, essentially, you can build a language model of them in the sense that you can generate words one at a time, right? So all you're doing is do some special case operation at the beginning, so that you can, maybe give a special token instead of a word. Now we have a, instead of just the words in the vocabulary, you can have some special extra words which kind of indicate, okay, this is the beginning, this is the end, this is the, start of the second sentence, and so on. There you'll see some instantiations like this next lecture also. So you basically somehow you need to add that this is the information that is provided to the first RNN cell. So RNN cells are this one, and then given this and the input, it should produce the first word. Okay. Now this is still a supervised learning problem. It's not generative AI. Okay, it's a little bit simpler than that. So all we're doing is in the training time we actually have an image and a sequence of words. Okay, we already have these captions. Okay, so and again for the we need to go from image to vector. We can use a pre-trained CNN, just like less than 18, less than 30, 34, whatever is the number. So what's the special operation? So actually, let me mention this. This is actually a CNN that won or came like in the top 3 in 2014, 2015. It's called VGG-NET. Okay, so the VGG stands for Visual Geometric Group. It's a research group in Oxford University. So anyway, so you can get an embedding from any such thing. It doesn't have to be VGG, but you get an embedding just like you did in assignment 2. And then the special starting case, instead of just doing concat or some transformation like this, which you saw in the RNN documentation as well for PyTorch, you just have an extra matrix the first time. Okay, so you get the embedding type, another linear transformation is added together with the previous RNN computation. Okay, so that's the only change. And after that, now what's interesting is going to happen is with this you get a distribution over words, right? So you want to create so you got a hidden vector, some hidden vector. From that hidden vector, you want to get a distribution over the vocabulary, so that you can actually sample or you get the highest probability word, and then you say that's the first word. Okay, so this first word, how do you choose? Is it a random one from the distribution of words that you get, probability distribution that you get over words, or is it the max probability that's a design choice? But once you do that, okay, here I'm just saying you sample instead of taking max. Let's say you do that and happens to be straw. If it's not straw, so while training time you actually do cross entropy loss to see that if it's not straw, then you incur a loss anyway. So let's say you sample in straw. Now you pass this as the second input, take the second, this hidden vector as the input, and now produce the second word. Okay, so it's a step-by-step process. It's like you can't, you're not putting all the inputs together. Okay. So and hopefully you'll either you want a short caption, or you actually see some special token like end token or end word, and then you stop. Okay. Any questions about this application? So given now the RNN discussion or sequence modeling discussion, this should be now okay. This seems feasible to do, right? Okay, so next look at one other example, auto reply. I guess most so some of the big vendors have this feature, right? They generate the answer for you, and they just like You just take the answer and say yes, right? But auto reply and all these other ones have the same kind of architecture, and you'll do one of these applications in the assignment 3. Okay, so auto reply, translation, summarizing, speech transcription, and question answering. Okay, these are all supervised learning problems. You need to have annotated data. You need to have those pairs beforehand so that you can train these models, and you can train the RNNs to do this. So auto reply, right? So basically, given some text as input, you want to generate some text as an output, right? So this is the options that were shown in this illustration. How do you do that, right? So I want to stop kind of at this example. I mean, there's a little bit more detail to this. I'm going to revisit this example next lecture, okay, where we're going to enhance this. But let's say, how do you want to do auto reply? One naive way to do this is with RNNs is you take the sequence of the input email, keep passing it on, get the hidden vectors, ignore all the hidden vectors up to the last one. And now you follow exactly the image captioning idea. You have the hidden vector from which you need to first generate first word, and then the first word can go, actually in this example, they're not even doing that, first word, and directly we are saying we'll not pass any word and we'll just generate the second word and so on. This seems like a naive, bad idea. We should actually pass the first word. Let me just switch to that. Just as the image captioning situation, generate the first word, pass it to the next one, generate the second word, pass to the next one, and so on. Okay. So this seems first version was actually pretty bad. So let's say this is the second word. This is the version that you can intuitively think of. You can think of this whole input getting compressed with this hidden vector, which is going to lead to the output, because the output process is a little bit iterative, right? It's sequential. Because the input process is not really sequential. You can give all the input at the same time. It's just all, at the end of the day, you just care about this hidden vector. Okay? So they can call this part the encoder and this part the decoder. Okay? And you'll see this encoder decoder style pattern also in some in next lecture's architecture, which is the transformer architecture. Okay. So yeah. So one thing I wanted to mention about the image captioning as well as here is the choice of, if you sample a word, okay, you could end up with a bad word. I mean, like a suboptimal word for the first, from the first sampling. Right? Then if you choose a suboptimal thing, then you will get some other suboptimal thing. You are basically highly dependent on choosing the right things at every step. Okay. So how do you counter that? There is this idea called beam search decoding in signal processing. I don't know if anybody has done electrical engineering before, but basically the idea is currently we are greedy. We're not correcting for any mistakes. We're just sampling a word and just using that word next time. Okay. Or you could do just picking the highest probability word. That's also very greedy, right? So you just pick the highest probability word. It just happens that prediction for the highest probability word is suboptimal. So instead of that, it's a very simple idea. Beam search decoding is just a way to do that decoding process, but keeping track of some extra candidate, outputs. Okay, how do you do that? So input is X. Instead of just focusing on the highest word or one sample, you can focus on multiple samples or the top K or top 3 highest, for example, in this illustration. So you remember the top 3 highest words. And then you see, okay, given each of the top 3 highest words, what's the next word that follows? Okay. But if you just do this naively, it's going to branch out like anything, right? But what you do is you prune also. You just remember maybe the top 10 such trajectories. Okay, so that's called beam search decoding. So you just remember that, okay, maybe high had a probability 0.8, yes had a probability 0.19, and this has a probability 0.01 or something. You just remember that although this had a probability 0.8, maybe the next words that we are seeing have probability 0.001, 001, and 001, let's say. Then the joint, joint probability, you just multiply these two, is going to be low, so that this trajectory may be, may get downweighted later. Okay. So you're just relying on not being greedy. Greedy just means I'm myopically picking the best or one sample and just moving forward in terms of decoding. Okay. So this is just an engineering idea. I mean, it has obviously roots in signal processing where we do this we used to do this for audio signal processing anyway. before, just auto reply application here. So that's the extension. And yeah, next extension we'll not talk about today. Yeah, let's actually stop here. Yeah, let's just stop here. Any questions about the application? We just saw a sentence classification that was kind of pretty straightforward, and then we saw image captioning, and then we saw this auto reply. Auto reply is just an example. It can be also this translation example. We'll see translation examples next time, and we'll also see another extension, another improvement to this architecture, this encoder decoder architecture that we saw next time. Okay, before we get into the next generation models. Okay.